Good morning, everybody, and welcome to Houston Techfest 2020, the virtual edition. Before we get started and continue on in the third session of this track, I want to call your attention to the Q&A feature. In the upper right-hand corner of the interface, you'll see two question bubbles, one with a question mark in it. That's where you'll be able to ask questions. Feel free as they come to mind. Go ahead and ask them there. I'll be curating those and asking them to our presenter at different times in the presentation and then wrap up at the end. And so please feel free to post those anytime. Also excited to let you know that there's a link inside the Q&A section right now. Code Magazine is giving everybody a free subscription. You can claim that at the link there, as well as the session recording will be available at houstontechfest.com. Now, without further ado, we're proud to present Ron Dagdag, who's going to be talking to us today about developing a Spidey Sense and anomaly detection in IoT apps. Ron, take it away.
Good morning, good afternoon, good evening, everyone, wherever you are in our virtual world right now. My name is Ron Dagdag, and I will be talking to you about developing Spidey Sense anomaly detection for IoT applications. Hopefully everyone's doing good today. Let's talk about Spidey Sense. Let me tell you a backstory how I chose this title for my presentation. I have a 10-year-old kid, and ever since he was 2 years old, Spider-Man has been part of our growing up, right? I mean, we have a Spider-Man shirt, and to celebrate today, actually, I have a Spider-Man shirt with me that talks about Spidey Sense. So I thought it would be interesting. And what is Spidey Sense? It's that tingling sensation on the back of Peter Parker's skull that tells him and have that ability to sense and react before something bad or danger is going to happen. It helps him increase his ability to detect evil and even his clones, as one of the movies, and then helps him navigate if he is impaired or disoriented or unable to see or hear around him. It also aids him to discovering, secret passages or lost objects, finding stuff around. And I think it helps him change costume too, from Peter Parker to Spider-Man. If someone's watching him or something, it helps him fire his web shooters, swing instinctively. It's that fifth sense, if you can think about it, sixth sense. In the real world, there is, real spider sense. Spiders have this hyper awareness. It's because of the long, thin hairs called trichobothria that is, around their body that can detect low level of vibrations through their web. It can detect even faint sounds, and that I thought that was very interesting when I'm researching about Spider Sense, and I didn't know that even sound, they can even detect sound through that, and it can also a small insect. You can detect small insects moving around 3 meters away, and to think about how small a spider is, 3 meters is like a big deal. And of course, if we have web developers here and when you're starting your career as a web developer, it feels like this. You're trying to shoot things around, try out different, how you would develop your website, and nothing comes out properly as you expected. So for me, Spidey Sense is that gut feel, that certain vibe and feeling. It's that intuition that tells you, hey, this project, there's that level of success or level of failure. Through time, you learn that. It's like the different things that you accommodate or you learn from the past. I would call it battle scars if you're doing a lot of project development and all that too. Yeah, it also helps you discover blind spots in the project, right? Through time, you would identify, hey, we didn't talk about this part of the conversation. It's not in the specs. What's going on? It's that learning from the past that gets you that Spidey sense feeling whenever you're working on a project or when you're going to a certain scenario. If you think about it, a lot of the professional players, baseball players, basketball players, they don't think about what's gonna happen next. They instinctively know how far, what's the best way to shoot the ball or catch the ball, and they can think, it's part of their senses as it becomes normal for them. So the way I see it in the IDE, all right, the interface for us as software developers, there's that part where in our language there's a low-level programming language. That's when you have assembly language and all that, and you have the compiler that helps you translate from the high-level programming language to the low-level programming language. So high-level programming language would be like JavaScript or something, C# or a lot of the VB script and all that too, right? And the lower level you go, the harder it is to program or to identify bugs or issues. So in our lives, we also think about it in terms of our human beings. We also have instincts and intuition, like you have your, you don't even have to think when you walk anymore because you learned that in the past. You have your intuition and instincts that helps you guide through. Sometimes I go to work, right, and I don't even know which route I took. I was able to get to work. I was able to drive, and I can tell you what happened or what I was thinking around that day, which is about insights. But I can't tell you, like, did I, was there another car, or did I stop a certain, it's just that it becomes normal for us. It helps us with that intuition and instincts. And guys, if you have questions, feel free to put them in the chat. I'll be happy to discuss more and answer them for you anytime. So what is our agenda today? Today we're gonna talk about anomaly detection, specifically in a time series anomaly detection for Internet of Things. I'll do a little demo and have some takeaways. So anomaly detection is identifying unexpected items or events in our data sets that is different from normal. We live in unprecedented era or days, especially now that we have the COVID and all that. It's an outlier. It's not something that we, there's that new normal, right? That all of us have to adjust to this new normal that we live in because of the pandemic. And so assumptions for anomaly detection would be, that it very rarely occurs in the data and also differs from normal instances significantly. So there are causes of outliers. It could be artificial error or a non-natural or a natural one. Let me talk a little bit more about that. What causes different causes of outliers? One is data entry errors. You all heard of the term fat fingered, right? So whenever, especially in spreadsheet, 100,000 versus 1 million, that makes a whole lot of difference if we're talking about sales, right? In sales numbers. So that would be a data entry error that might cause an outlier. Another one is a measurement error, right? You're supposed to have measured it in centimeters and put the inches instead. So those are type of measurement errors. Experimental errors is when you have collected your data instead of sequence of events. You started to collect your data late in the sprint cycle, meaning you just cram all your data at the end. So that might cause issues with your data. Another one is intentional outlier. A good example of that is when someone reports, alcohol consumption, especially on teenagers, right? Most likely they would say they don't drink as much, even though compared to the real truth. Another one is through data processing errors in how you extract and how you you read data from the database, and it could be that it's missing some of that data, or how you convert that data from one medium to another. That can be issues also for data processing. Sampling errors would be a good example of that, is the reporting heights of all athletes and included, basketball players, and the height gets skewed because of that. So it depends on what you're trying to sample too. And then of course the natural outlier, when it's not artificial, it's the real data that's causing the outlier. So at the end of the day, what we're trying to do is you have your data input as you receive it, and we're trying to identify, is this data anomalous or not? And there are some instances, you see that the defective means it's anomalous, right? The defective data, and some of them are good data, but which specifies here as blank. But there are some instances where you'll be able to detect, most of them are the defective ones, but there are instances that you may detect that you may not be able to detect that it's anomalous, maybe because of the rules, or maybe whatever logic we're trying to identify may not be good enough to be able to detect. But sometimes it's the other way around, where you think the process thinks that it's anomalous, but it is not. So that's when you look into the confusion matrix, which one is a true positive, a false negative, or a false positive, or a true negative, to determine accuracy, precision, and recall. And of course, one term for looking if it's anomalous or not is, is there that needle in a haystack? And there it is. Isn't that obvious? So methods of detecting anomalies or outliers. One thing you can use, or three things you can do, is through a rule-based system. Another one is through statistical techniques, or through machine learning. And I'll go through each one of those. Rule-based systems is when you specifically identify the rules and, like a threshold or limits. Like, for example, you're trying to set the temperature of your, when you're cooking your barbecue, if it's too hot or too, if there's that certain limit, you want to be alerted, or if it's too low, it may not get cooked properly, those kind of things. So where you assign the threshold and limits, and at the end of the day, the industry experts are the one that can detect known anomalies, because through time they know, and through experiments they know what are the the thresholds and limits for specific items you're trying to track. One of the disadvantages of using a rule-based system is it does not adapt as patterns change. Because once you set the rules, even if you have a checklist or not, it does not adapt until you go label them again, or you create your other checklist to say, hey, the threshold had changed. And of course, that takes another whole set of process that you have to redo on a rule-based system. And I believe in this quote from Julius Caesar, that experience is the teacher of of all things, and that's when we know that anomaly detection, all these different things, is based from what happened in the past or what we've learned from others that help us identify outliers. Another one is through statistical techniques. Statistical techniques would mean when we flag those data points that they deviate from statistical properties, like deviate from average, like mean, median, mode, or quantiles. Sometimes we use rolling average and moving average to identify those anomalies. And one good example of use of moving averages is Kalman filters. If you haven't heard of that, it's it's what they use to an algorithm they use to have cleaner sensor data. Because typically sensor data would be more noisy, and using Kalman filters, it averages out as a filter. You can also use histogram-based outlier detection, so it's more statistics-based. And the good thing about statistical techniques and the advantage of that is it's easier to interpret. There's existing formulas out there that you can use compared to machine learning methods. So let me go back and try to give you an example. When do you use an anomaly detection technique, or when should you use anomaly detection than a supervised learning versus supervised learning type? If you have a very small number of positive examples, meaning anomalies, if you have a very small number of anomalies that you're trying to detect, then it makes sense to use anomaly detection formulas. Supervised learning is when you have a large number of positive and negative examples, more like equal from each other. That's where it's best, that it works best. When you have a large number of negative examples, of course, and a small number of positive examples, that's when you use anomaly detection. And there are some instances where you have not really have a good example of an anomaly yet that you haven't discovered, or even the expert hasn't discovered yet. That's when you use anomaly detection algorithms. And of course, for supervised learning, most likely they'll be similar from the training set. So how you would know which one to use? So for anomaly detection, it's great for you're doing fraud detection, when you're trying to determine patterns. Right? Most likely you've experienced this in the past, where you're using your credit card and then you go to a different county or different state or different location, and suddenly you get triggered, hey, your credit card is blocked or something, because of these fraud detection, because it's out of the usual pattern. It's also good for manufacturing and machineries, because we know in manufacturing you have an engine that goes back and forth, right? Or a conveyor belt, it goes back and forth, and if there's something wrong, if there's a cog in the wheel, right? That's when it becomes anomalous, that you're not getting the same data set. Monitoring data centers, especially for Internet of Things, also are at the edge. Supervised learning is good for email or spam classification. When you're trying to identify, is this email spam or not, right? The reason for that is there's a lot of examples out there that is existing for identifying spams. Weather prediction, there's, of course, here in Texas, it feels like we only have two types of weather sometimes. It's either too hot or too cold for us, or not too cold. We only have snow here in Dallas area once a year for us. Not sure in Houston. I think sometimes it's already an anomaly when they have snow in Houston. Cancer classification also is a good candidate for supervised learning because it, the scientists already determined this type of, cancers. So for machine learning methods, as I research this, there are different algorithms how you can use to identify anomalies. Supervised could be supervised, unsupervised, or self-supervised. Supervised would be more for, decision tree algorithm, forecasting, LSTM forecasting. Unsupervised may be using k-means, and self-supervised may be for LSTM autoencoders. So just to give you like an idea of the different algorithms that out there that you may use for detecting anomalies. One of them is using density-based anomaly detection. So looking at this graph on the right side, where the green are where the reds are the anomalous one. You see how they're clustered with each other, and that determines that they're normal, and the red ones are abnormal. Clustering based also, where you specify groups or clusters. Sometimes we can use also Gaussian distribution, where your normal, they are in the same Gaussian distribution, but anything that's an anomaly would be outside of that distribution. You can also use support vector machines, anomaly detection for machine learning. How you would do this? One good example is you draw a line right in between the what's anomalous and not. So what I'm trying to get at is there's a lot of different algorithms out there, a lot of research regarding implementing anomaly detection. Today I'm going to focus on how you would use it for Internet of Things and the advantage of using it for Internet of Things application. One of them is because Internet of Things happened because it's cheaper to produce sensor data, right? There's lots of machine, right? I mean, you think about your phone right now, how many sensors you have on this phone and how much data you can collect from your cell phone. Another one is increased data speed with the improved networking. We think about, the upcoming 5G, and it's already here, and how it would increase the data speed. So with all that, the risk environment that are, because it's moving fast and it's more and more like we need more use from our phone, failures are not tolerated. There are, as we move to the next generation of Internet of Things application, it's becoming part of our livelihood or our lives. And so when it doesn't work, it feels like this, right? It becomes an internet of broken things. One good example for me is sometimes our common use for Alexa in our house is to turn off the TV, and of course it's gonna talk to me now. But yeah, and sometimes I get frustrated because I can't find the remote control, and I get used to like, okay, I can turn off my TV by saying that magic word. But if that magic word doesn't work, then yeah, it does kind of have to find the remote now and go back to the old ways. So artificial intelligence of things, and it's more and more happening every day. That like what I talked to you about a few minutes ago regarding our insights, which has our brain has the interpreted module to do some work. So meaning we have data from our from our instincts and intuition. It goes through the interpreter module, and we have these insights and aha moments, right? So also for the artificial intelligence of things, it's when you have all these edge gateways or real-time sensor devices that collects data for you, and then you send them up to the cloud, all these different data information, and be able to visualize and add business intelligence and dashboarding because of all the data that you've collected. So each part of from the edge gateway to the cloud device twins to the business intelligence, each part has that artificial intelligence that you can integrate to produce your data, to have cleaner data. So time series in anomaly detection, there are 4 different types you'll be able to see. Time series meaning certain date and time, and then the sensor data, right, or the data you're interested in collecting. You'll see that outlier, spike, level and shift, pattern change, and seasonality. Outlier would something like this, right? Through time, you're collecting data, and then suddenly it spikes up. That becomes an outlier, right? Do you care about reporting that error message or not? But it's up to you. But this is how you would, this one way that you'll be able to see that. Another one is through spike and level shift. Like, your sensor data would be receiving at a certain level, and then suddenly it started receiving at a different level. And so something happened in between here, right, that you might want to look into. Another one is through level shift, where it's, you see that pattern, and then now it does not go as high enough. That's another level shift type. Or it could be a pattern change, where there's a min and max that you're supposed to be receiving your data, and then suddenly you're receiving it less at a certain pattern. Seasonality can also affect how you might want to detect. We all know that around Christmas, shopping happens, or a lot of the retail industry, they receive a lot of orders or a lot of traffic. Also, ice cream sales happen around summer in the same way as seasonality changes. In this case, there's that ups and downs through your machine, and suddenly you're receiving this much data. So that is an anomaly. Think about it, if this is sales data and you're kind of expecting a certain amount of sales data, and suddenly something happened and needs to be investigated. Any questions so far? Good?
Yep, there have been no questions so far.
Cool. All right, so whenever you're working on an IoT project and there are production issues, it feels, since you're receiving data and you're gathering data, it's just streaming data, production feels like this, right? Feels like you're trying to stop a train. For Internet of Things, data set, you would hear this, what we call IID data sets, which is identically distributed and independent when you're working with anomaly detection. Identity distributed means that the overall trends, that the distribution does not fluctuate, meaning it's the same probability of the distribution, meaning where you collected your data, like in this case, you collected your data through this roulette. They all belong to the same roulette, right? And another one is through independent events that in not connected to each other, meaning when you throw the ball in this roulette, when you try to measure again, you pick up the ball and you throw it again, right? It's independent from one sense, from one collection from the other, that it does not depend on the previous one. So, like for example, when you're collecting temperature data from your sensors, each time you collect, it's independent from each other, that it did not depend from the previous reading. Time series anomaly detection algorithms that is available out there, where you'll hear about spikes and change points. Spikes would be temporary burst of anomalous behavior in the system, and change points would be that level changes and trends. So for anomaly detection in Internet of Things, where we would use it in the cloud scenario, where you have your this is your, like in this case, the example that I'm showing today is on the Azure streaming analytics, where this one is in the cloud, where you can use ML.NET in your edge devices to improve your anomaly detection. And then on this case, also for the dashboards, you can use cognitive service to improve your anomaly detection, or to use anomaly detection in your dashboard or for your business intelligence or Power BI. So let me kind of show you a little bit about some examples on how you can use anomaly detection in an so here's an example, or like a kiosk example that is available out there, intelligent kiosk example that is open source, where you're like in this case, there's AdventureWorks bike rentals, and you're collecting data, and you see these dots right here. It tells you that there is an anomaly, and this is out of range because of that. And so this data right here, this data set, is based from the history, and this span is that amount of time, amount of data that you collected to be able to detect that this is anomalous or not. And of course, sensitivity here identifies how sensitive the data collection is. The lower your sensitivity, that means the more anomalies you would be detecting, and the higher it is, the more anomalies, the less anomalies that you would be able to detect. In a manufacturing scenario, would look something like this. You have your machine that runs every certain number of hours, and you maybe turns off after a while, and if there's an anomaly in the collection of data, it would identify that it's anomalous or not. Cool. Let me go back to that presentation real quick. Okay. So ML.NET is an open source cross-platform for machine learning framework for .NET. It's specifically made for .NET developers. The good thing about ML.NET is it's not just you can deploy it on premises. It's also, you can deploy it in the cloud, or any cloud for that matter. You can also deploy it on your edge devices too. It's actually built for C# and F#. People that have F# and C# skills that want to integrate machine learning into their .NET application, and the machine learning or data science experience is not required. So there's already a time series catalog that you can use in order to implement the algorithms for time series of anomaly detection. And the one that we're going to be using today is the Detect IID Spike, which can detect algorithms and predict spikes instead of change point. Let me try to demo that real quick. As we go. All right. So think about this. This is my time series data, right? Raspberry Pi that I collected the temperature data. So I have my temperature data here and the time that I took my temperature, right? From that device. And of course I collected a few times every minute. At the end, notice that my number right here, I made up these numbers, I changed it just to identify, hey, this part right here, this is anomalous, right? Because it's way far or way higher than the usual. So our algorithm should be able to detect that these are anomalous. So that's my data set. So this is my .NET program. I would like to receive, map my data from that CSV file, the temperature data. And on here, I read that CSV file, and I'm using ML.NET to be able to connect and use that algorithm, right? Algorithms, the time series anomaly detection algorithms. In order to do ML.NET, you have to use Microsoft.ml and Microsoft.ml data that you're incorporating it with your project, right? In this case, I reference Microsoft.ml and Microsoft.ml time series in order to access to that time series catalog. So once I set that up, and by the way, these example right here is available on that on GitHub. I will send you the link later on in my presentation if you want to review it later. But what it's doing right here using ML.NET, I was able to load from that text file, that CSV file, our data. And on this part right here, I am constructing the pipeline to convert that input temperature data to convert it to a model. So it right now it's listening. It's reading it as a string, because right now the data is a string variable, and converting it to a double so that I can use it for the anomaly detection. So once I was able to load that, get the transform data, I would pass it to this detect spike algorithm, which uses the ML.NET context platform right here. So ML context.transform.detect IID spike would read the temperature column and would output the prediction based from this category, this input right here, meaning looking at the last 25 items for each line on this CSV file, right? Look at the last 25 items and detect if that item is anomalous or not. And if it finds out that the confidence is more than 95%, identify it as anomalous. If the confidence is lower, then it's not anomalous. So in order to use this in ML.NET, you would create an empty data view to create, it's always that pattern between transfit and then transform. You'll see that in a lot of, there's that, when you train your model, there's that dot fit. And when you're ready to work on use that model, you would see dot transform from that model. So once you transform that data, you read through the results and it would identify if there's that spike or not, or if it's anomalous or not. Let me try to see if I can run this real quick, just to give you example what it would go through. So there's my data that I loaded with my pipeline. See that fit and transform. I pass in my data to transform it, or to create the transformer, and then from that transformer, it would create this transform data. And then in this case, this is where I would use the detect IID spike, run it through. And then now I have my predictions, a list of all the data set. Let me see if I can run it. Let's see, from this example, it reads through all the sensor data. And at the end, over here, it would identify, hey, that is considered a spike, because you have your kind of like your data range here, and then boom, it increased, and so that's anomalous. So here it wasn't able to detect because the confidence level is 0.06, and we specify 95%, and so this is so it's like the other way around, right? If it's less than 0.05%, that means it's anomalous. If it's more than 0.5%, that means it's normal, and that's where. So it's close enough, but if I specify my confidence level to 90%, this one would be detected as a spike, and this one too. So you have to tweak those numbers until you get it right. Cool. So that's a small example of how you would use anomaly detection in ML.NET with the new version that just came out for ML.NET. There's new algorithms that would detect seasonality and removing the seasonality from time series for your anomaly detection. Okay, moving along. This one you can also use anomaly detection through Azure Streaming Analytics. I'm not going to focus on this one today, but I wanted to kind of give you how you would use it, using how you would use this in the context of stream analytics. So as you receive your data from the cloud, or you can actually deploy these on the edge now too, is you have these algorithm called anomaly detection _ spike and dip. That's part of your streaming data query, where you would identify the duration, how far back you would look at from your data. In this case, I want to look at 120 seconds as the last 120 seconds as I receive this streaming data. And if I'm confident, 95% confidence level, so that means, like on our previous slide, if it's less than 0.05, that means it's anomalous, and then display it. So that's one example how you would use it for your Azure Stream Analytics. Another one is through change point where your data and then suddenly drops. How you would use this. So what you can do is you can ingest the data, go through IoT Hub, and from IoT Hub, go through Stream Analytics, and you can do your real-time stream scoring and there. And then if there's an alert, there's an anomaly, then you can store it in a blob storage or send it through Azure Functions and how you would send that alert. So that's one way to set up your anomaly detection if you have streaming data. One feature in Azure that you can use anomaly detection is through Azure Cognitive Services. At the end of the day, it's just an API call instead of implementing the different algorithms for Azure for anomaly detection, right? So part of Cognitive Services is this anomaly detector right here. There's also personalizer and content moderator, but we're going to focus on the anomaly detector today. Anomaly detector is a RESTful API that can monitor and detect abnormalities. You can also fine tune, same way as how we used ML.NET. There is where you can identify boundaries and expected values. Okay. You can either have it as a batch or you can detect anomalies as they occur in real time. So how it's doing it in the background is it would extract features from your data, and then there's different types of algorithm of how it would detect. It also includes seasonality. So it automatically does this for you, and these are some of the algorithms that's already implemented for you that can detect anomalies. Don't ask me how to implement all those. I know how to use the API. Let's do a quick demo on how you would use this. So right here I'm using .NET, but I have a Raspberry Pi here with me. Okay. And this Raspberry Pi, let's see if I can, you guys, right there. So this Raspberry Pi has a Jupyter notebook installed on it, and it's running .NET Interactive inside that Jupyter notebook, inside that Raspberry Pi, so that we can, connect to that browser, from our browser, connect to that Raspberry Pi and run some .NET commands. I already ran few. This is how you would use .NET Interactive. You remember .NET Interactive, you can run it through Jupyter Notebook, and if you're a .NET developer, notice that there's no main. it's a way you can interact or run programs through those different cells, and as you go through each one of the cell, like how I ran this. So like in this case, I want to use and turn off these LED sensors, and this is that algorithm that I was able to do that. So if I want to, in this case, right, if I want to turn it to green, I can just say, I'll color that green. There are all my LED lights have turned green. So I'm going to turn it off, right? So it's a different way of paradigm of programming because it's interactive. And so like in this case, I'm reading the temperature data, right? And from that temperature data, I collected them and it looks something like this, right? It's a time series data where I collected it at that time, and this is the sensor information, and I collected it 15 times. So I'm using asynchronous streams to collect my data. So at the end of the day, once I collected that data, I added this NuGet package called Anomaly Detector. So Anomaly Detector is available. There's different packages, or you can use it in C#, JavaScript, because at the end of the day, it's a REST API call, right? You can use it in Python. I'm using it through these NuGet package, cognitive service.anomaly detector. So there's, you need in order to get the key and the endpoint where to connect to that API, I added that link here because you would need the endpoint, which server you need to connect to, and also the subscription key in order to connect to that API. So once you set that up, at the end of the day, what we're trying to do here is we get the series of data, right? And I'm kind of cheating here because I have a list of all my temperature data, right on here. And on the last one, I want to, my last sensor, I want to put 200 instead of 100, like in that case. And since I got my data right there, let me see if I can rerun this. If it's more than a certain amount, right? If calling the API, it returned that it is anomaly, I change the color of the LED matrix to red. So that's what I'm going to do here. So get the data, call it, since the last reading was an anomaly, I change the LED matrix to red. And of course I want to reset it back because it's hurting my eyes, because that that red color right there is big alert. So that's where I turned it on. Okay, let me go back. Isn't that cool? I was able to control a device from the browser through, through the power of Jupyter Notebooks and ML.NET and cognitive services too. So where you can use Anomaly Detector, you can use it for C#, JavaScript, Python. There's also a way you can package them in Docker containers. There are instructions out there you can incorporate to your Power BI. So if you have a sales report that you want to find anomalies, or some data that you want to showcase anomalies, you can also incorporate it to your Power BI. There's also a way you can incorporate it with Azure Databricks for streaming data. So at the end of the day, the best superpower you can give to any of your IoT project is we call anomaly detection, which is I consider as that's certain Spidey sense. And if you're interested in learning more what I demoed today, and if you want to get the code, here's a link. And I am open for questions. Thank you very much.
Awesome, Ron. I greatly appreciate it. So the only thing that we've got in the questions block is a whole bunch of praise for the talk, saying that it was great and that it provided a lot of value.
That's great to hear.
And so I will just say thank you to everybody for attending, and Ron, thank you for sharing. This was actually really cool. Recording of the session will be up on HoustonTechFest.com soon, and hope everybody enjoys the rest of Houston Tech Fest. Have a great day.
You too. Thank you.